this example. Again, this is f, some things to remind us and jog our memories. We know that certain things are like true, like when f is increasing, that means the derivative is positive. When f is decreasing, the derivative is negative. And then we also know it affects concavity. As the function is concave down, the derivative will be going down. As the function is concave up, the derivative will be going up or increasing. So when I start these problems, like if I'm going from f to f prime, I know there's some really easy things to do. And that's where the derivative is equal to 0 at. So like I can see at -5, there is a horizontal tangent. So I know that at -5, the derivative is equal to 0. I can also see here that the graph goes a little bit horizontal at 6. So I know that at 6, the derivative is also equal to 0. And then this one also has kind of a weird thing going on. This whole section, like a little bit after -1 all the way up to 2, that whole section has a slope of 0. We know that the derivative is the slope. So I know that along this whole section, the derivative is equal to 0 as well. And so when it comes to help us break it up and kind of remind ourselves of the different pieces, I like dividing my graph up into sections. So I first divide it up where it changes from increasing and decreasing to kind of get a view of it. I see it's increasing that whole section. And then I also split it up from where it's concave up and concave down. So I see this first graph is starting to be concave down. Somewhere around this area switches to be concave up. There's the end of the flat section, concave down. Then it looks like at 6 it switches to be concave up. So eventually my goal is I hope that you can just like look at this and immediately start sketching it. I do think it helps to write stuff out first. So we're going to talk about like what f prime is doing. So remember, when the graph is increasing, f prime is positive. When when the function is decreasing, f prime is negative. So then I have this last section, the graph is increasing, so I know I have a positive derivative and a positive derivative. And then we can also talk about concavity. If the function goes up, your derivative is going to be increasing. I'm saying all sorts of things backwards. When the function is concave down, the derivative is decreasing. So this first whole section that's concave down, the derivative is going to be decreasing in that area. When the function is concave up, the derivative is increasing. No concavity for the flat section. Concave down, the derivative is decreasing. Concave up, the derivative is increasing. And then you just want to kind of draw something and match what we're looking at. So I'm going to go back to my orange pen. I have a positive derivative that is decreasing. Then a negative derivative that is still decreasing. Then it's negative and increasing. I'm going to go join up with that piece. A cusp on the function, we know the derivative is not defined. So I'm actually going to put a jump right here. So at that cusp, it has a slope of 0, and then it has a steep positive slope. So I'm just going to pick like, that looks like it's about 2. It looks like a pretty steep slope. So I'm going to put it as a positive slope. And this slope is always positive. So I'm going to draw my derivative always greater than 0. But it does kind of decrease first where the function is concave down. Then the derivative goes back up when the function is concave up. So that's what we looked at yesterday, going from f to f prime. This graph I did in orange would be an actual graph of the derivative. Any questions about that graph of the derivative before we switch it up and kind of go in the reverse direction, going from f prime back to f?
Yes.
Go ahead, Mitchell.
I believe you explained this yesterday, and you said that it was based off of the table.
Mm-hmm.
But could you just go over why when f prime is positive, it's decreasing, and then it's
I'm
negative.
not gonna go over the why right now. We can do that later, but like I'm just gonna say it again, and it's kind of a bad answer right now, but like these three statements in our chart are all interchangeable. So like when I say F is concave up, that means the same thing as saying F prime is increasing, which means the same thing as saying F double prime is positive. Like those three statements are interchangeable, whether we're talking about F prime or F double prime, but they all mean the graph looks something like this. Whereas when I say like F is concave up, that means F prime is decreasing, which means F prime is negative, meaning we look something like this. The short answer as to the why, I'm not going to get into it again right now, but if your slopes are in this case increasing, like it's going to make a concave up shape because the slopes are basically growing in value. If the slopes are decreasing in value, then it makes more of the bowl shape, is the why. But the short answer is just note this chart.
Okay.
So like going from that chart, kind of to segue into what we're looking at today. Today we are going to look at going from F prime to F. So I used the same graphs that we did yesterday, just changed them. So again, we are no longer looking at the function, we are now looking at the derivative. For me, when I draw a function from the derivative, it's a little bit easier. So one, like cusp and corners, like don't really do any weird stuff on the graph. Like we don't have to worry about doing jumps or anything like that. Also, when you are going from F prime to F, the specific F value, specific Y values don't matter. Just the shape. And the reason why, like if I just give you the derivative, we just know like, hey, this function is increasing and concave down, but we have no idea where it's located at. So we won't have to worry about like where we put this on the graph. We just want to make sure that the shape matches what it needs to. So I do a similar thing when I go to graph these problems. So again, this is the function y is equal to f of prime. So we are literally looking at the derivatives. So things that I want to kind of look at, I'm still going to divide it up into sections to help me out. Again, eventually a lot of you will not have to go through these first beginning steps if you get better at just like seeing it. But when I'm looking at this, I see that this graph starts off all above the x-axis. So like we're above the x-axis, above the x-axis, above the x-axis. I also see that on this other end, we're also above the x-axis. And again, this is the derivative. So we want to think to ourselves, when the derivative is above the x-axis, basically when the derivative is positive, what do I know my graph has to be doing while the derivative is positive?
Is it increasing?
It would be increasing. So basically, if I'm dividing it up into sections, like I have no idea what this original function looks like. I just know that this is the derivative of that function. I know that this first section, whenever I'm less than -2, I know that this will always be my f this time. So I am drawing f, the original function, not f prime. I know that it's going to be increasing while the derivative is positive. And so I can see basically on the far left-hand side and the far right-hand side, this graph is going to be increasing. Then I also see the derivative is below the x-axis, meaning that the derivative is taking on negative values. While the derivative is taking on negative values, we know that the function itself is going to be decreasing. So it's going to be decreasing for that whole interval. I left this middle kind of interval a little bit blank between 3 and 6 because I see the derivative is on 0. If the derivative is on 0, what are we basically saying the function is doing between 3 and 6? What would it mean if I said the derivative was 0? What would that function look like?
A horizontal line?
It would be a horizontal line. So pretty much between 3 and 6, the entire derivative is always 0. So again, when we say the derivative, I mean slope. So like at 4, the slope is 0. At 5, the slope is 0. So basically in this part of the section, we know that we just have a horizontal kind of section on the graph. There are some other kind of things going on. Like these horizontal sections will kind of be weird because we can see the slope exactly. For example, I'm going to divide it up a little bit more into different sections. In this first horizontal section starting at -5, it's a horizontal line at -1. So I know that it is increasing, but I know that the slope is always a +1 because the derivative is just a horizontal line at +1. Same reason for this next horizontal section that starts at 0. It's horizontal at -2, so I know that the slope is like a constant -2 in that region. So I hope we're not too confused with all my markings on here, but let's go ahead and talk about the concavity, and then we'll be able to draw this out. When your derivative is decreasing, what is the original function going to be?
Negative.
Try again. So again, like right here, the derivative is decreasing. When f prime is decreasing, what does that mean in terms of f?
Concave down.
Concave down. So again, we want to keep kind of things separated. When I say f prime is positive, that means f is increasing. But if I say something like f prime itself is increasing, that means the function is concave up. So if I'm looking at different sections here, whenever my derivative is going down, my function is going to be concave down. Whenever my derivative is increasing, that means my function is going to be concave up. If the derivative is not increasing or decreasing, then it has no concavity, and that's why we're going to have like a straight line there on the graph. So again, when I go to draw this, I'm going to get like a nice chunky marker to look at it. The y value doesn't matter. You just want to pick a starting point and go with it. I see that I'm increasing to start off this graph with, so I'm going to start a little bit towards the bottom and then just kind of work my way from left to right. So this first section, it says my graph is increasing and concave down. So I'm going to draw a graph that is increasing and concave down. This next section is increasing, but it has a constant slope of 1. So I'm going to just draw like an estimated constant slope of 1. Then I still have a graph that's increasing, but now it's still concave down. Then I see my derivative switches to be a negative, so my function is going to start decreasing. The derivative is also going down, so my graph is going to be concave down. Then I have another straight line section where the slope is just a constant 2. Then I still have a negative derivative. So starting at 2 to 3, the derivative is still negative, so it's still decreasing, but now it's concave up. Then I have my horizontal segment where the derivative is 0, and then I have a positive derivative that is increasing, so my function will be increasing and concave up. So this is a possible graph of f. I won't say it is the graph of f because again, we don't know the y value, we just kind of picked one as a starting point. And again, this section is a straight line, this section is a straight line, and this section is a straight line. But all those other sections end up having some sort of bend on them, depending if the derivative was going up or if the derivative was going down. I'm going to give that a second to soak in your head. Questions are things that I can clarify. Or I can do the next example, and then maybe you have questions when looking at both of them.
So you said that the y value doesn't matter, and you could just go as high up or
correct. Like I just picked a starting point, and the reason why the y values don't matter, like in this first interval, I just knew that my function was increasing and concave down, but I didn't know like, is it above the x-axis? Is the function below? Is it on? Like I don't know where it's at. I just know that it needs to be increasing and concave down. So I just kind of picked the starting point and went with it. Let's try the second one. I think the second one actually works out nicer believe it or not, just because it is more of a smooth function. So I want to look at this one. So again, yes, this is the same graph we did yesterday, but now I am saying that this is f prime, and we want to graph f. So we're looking at f prime, and we want to graph f. This one, we have kind of less things going on, but again, we want to think about it. So this is the derivative. So how you're interpreting this, when the derivative is positive, this unknown graph we're about to draw would be increasing. When the derivative is negative, this unknown graph we draw is going to be decreasing. When the derivative is increasing, the function is concave up. When the derivative is decreasing, then the function is concave down. So again, it helps me to split this up into regions. So I have my first regions, I think about where it changes from positive and negative. I shouldn't use the word it, when the derivative changes from positive to negative. And then I also want to mark sections where the graph changes from increasing to decreasing, because that's when the concavity is going to change. And then I want to just figure out what f is doing as I work across the page. So I want to think about what f is doing. And again, if you just want to jump in and start drawing it, you definitely can. So when I look at this first section, I see my derivative is down here below the x-axis. Since the derivative is below the x-axis, I know the function's going to be decreasing. Is my function going to be concave up or concave down in that first section? Based off of what the derivative looks like.
Concave up.
It's going to be concave up, and this is where some students mess up. They're like, but Mr. Brown, that clearly looks concave down. And I'm like, yes, it does look concave down. The graph you are looking at is concave down. But we're not graphing the derivative again. We're graphing the function. Since the derivative is going up, we know the function is bending upwards. This next section, the derivative is now positive, so the function is going to be increasing while the derivative is positive. When the derivative goes up, the function is concave up. When the derivative goes down, the function is concave down. And so it stays concave down for that whole interval. Then the function is going to be decreasing again, decreasing, and then increase. While the derivative goes down, the function is concave down. While the derivative goes up, the function is concave up. And then I just start from the left-hand side. Again, the y values don't matter when you're going from f prime to f. You just want to pick something. So I see like I'm decreasing, increasing, decreasing. I'm just going to pick somewhere in the middle. I'm going to go back to green. So this function, we're going to start decreasing and have it concave up. So I'm going to be decreasing and concave up. Then it's increasing and concave up. Then increasing and concave down, decreasing and concave down, decreasing and concave up, increasing and concave up. And so that green graph would be an example of f. I'm going to connect this to something that Mitchell actually asked yesterday. He asked that sometimes when you go from the function, does the derivative, does it get more simplified? And my answer was yes, for a polynomial function, it does get more simplified. So the reverse is kind of also true. If you have a polynomial and you're going from the derivative to the function, then it gets a little bit more complicated. So if you look at this one, the derivative was like a cubic function, and now the original function is like something to the fourth power. But again, you can just draw it based off of what you know about how this function is bending and when it's positive and when it's negative. Any questions on that? All right, so tomorrow we're going to do justifications. I could start them today, but I'm just going to say we're going to do them tomorrow. Because there are certain ways I want us to be able to write in math. We don't write the same way in math that we write in an English or a history class. Again, it's kind of frowned upon in math if you give a really long explanation. There won't ever be a word count for me. In fact, the fewer words you can use, the better. So we'll do justifications and talk about that tomorrow. Your homework, again, everything you've been assigned is homeworks numbers 1, 2, 3, and 4. Now when it comes to homework 3, I'm still not asking you to do all of it. Basically, I asked you yesterday to do numbers 1 through 5, where you went from F to F prime. Today you can do numbers 1 through 5, F prime to F, just the second column of it. The second page of that deals with justifications, and I want you to save those justifications until at least after tomorrow. Again, looking at this full week, or next week as well. So we'll finish up the notes tomorrow. Monday, Tuesday, Wednesday is all review. I will have actual stuff we're doing Monday and Tuesday, mainly to focus on these justifications. I find that to be a challenge for a lot of students. I want to make sure we hammer that down. Wednesday, are going to start being asynchronous. Your Wednesday is just like your review day, except instead during class you have all day to basically review and ask me questions. Your quiz next week, this is the first quiz of the unit, is going to be on Thursday of next week. So pretty much Monday, Tuesday, Wednesday's review. And then after the quiz, we'll actually get to start learning rules to find derivatives algebraically instead of graphically, which I think a lot of you will probably like a little bit better. So with that being said, I'm going to go ahead and end class. Feel free to leave the meeting if you're good to go. If you want to hang out and ask any questions about